I get a lot of questions and comments about my videos. Maybe it's because I'm just not very clear with my explanations. I don't know. But I think it's normal. Everyone understands a little differently. So questions are always welcome. But I do get many, many of them, and I sadly just don't have the time to answer some of them. So every now and then I kind of gather a bunch up and I produce one of these question and answer videos, a Q&A video, actually once in a while. This is the second one that I'm producing. So today's questions, well, starts with a question that I asked and I got a lot of comments about, and that was the voiceover work on the latest version of the how to sharpen a drill bit with a bench grinder video. The response was yes, it was well worth the work. I had started producing videos years and years ago without really knowing what I was doing. Some would say I don't know much more now, but I think I have gotten better at it. But back then, the sound was absolutely atrocious. I had already tried to rework that video a few years ago, I think in 2016 or 2017, with mixed results. So I finally bit the bullet and did a full voiceover. Now that's a lot of work, and some people say, why don't you just redo the video? Well, I'm retired now 6 years, and I don't have access to a lot of that equipment easily as I did back in the day. So for me, in some circumstances, it's just easier to do the voiceover, even if it's a lot of work. So I may be revisiting some of my older videos and maybe doing voiceover work on them as well. The second question stems from that voice-overed version of the sharpening a drill bit video, because I received many comments and questions about drill bits and how they work, chisel edges, margins, cutting lips and whatnot, flutes and angles of attack and all kinds of things. Even one question about the thickness of the web of the drill that gets progressively wider as you grind it down. Now, you don't have to worry, because before you've ground off about the first third of a drill, your web doesn't change really that much. But sometimes you do have to thin the web to get a shorter chisel edge so that it will drill properly as it gets shorter. All these questions were looked at, I think, and well covered, I hope, in a video I produced some years ago about twist drills, how do they work, or metal cutting drills, how do they work. So here's a link to that, and that might answer a lot of those questions, because it's one thing to know how to sharpen a drill, and it's another to understand how it cuts. And if you understand the angles and the whys and the whatnots of the different parts of the drill, well, when you sharpen it, you can really do a better job because you know what you're up against. So something maybe you can go and watch. The third question, well, stems from the jigs and fixtures video. And well, it has nothing to do with jigs and fixtures, because I had mentioned that I wondered if there was some interest for a short series of videos on punch and dies and punch and die sets. And well, there does seem to be interest out there, because I received many comments about that saying, yes, that would be interesting. Now I designed some years ago, I designed many punch and die sets, but when you're starting out with students designing punch and dies, it's never a good idea to get into something very complex right off the bat. I mean, there's basic approaches and principles that have to be respected and learned. So I had designed a very, very simple punch and die set, a 2-station punch and die set for producing 1/4-inch washers using an arbor press, because we didn't start the students off on our 20-ton press right off the bat. It's something you work up to. So that was very interesting. Now I have the drawings of that project that I designed kicking around somewhere. I'll find them, and if I do, well, here they are. If I haven't, well, you won't see them right now. But if I do find them, I know one thing is I designed the project when I was teaching in a French school, so it will be in French, and I'll have to translate that. That will be coming up a little later, sometime after the holidays. My next video, and don't worry, is going to be the part 2 of the jigs and fixtures video, and we'll be doing in that a design and machining or making a plate jig, just a simple plate jig, but we'll see all the different things that need to be accomplished to get that done. Another question that stemmed from that jigs and fixtures video, well, I should really call it a request, was more information about plastic injection molding. Now, I had put a link to my basic introduction to injection molding video, but I do have more information about plastics, and that is plastics as a material. And it is a very vast subject. So I do have an introductory video to plastics, and that's the 4th video in my materials video. So it's the 4th part of that series. And here's a link to that. The next question has to do with this triangular tool post on my lathe. And many people have asked me, where did I get it? Well, I didn't buy it, I made it. I like the triangular design just because it gives me some clearance, and you're not always stuck up on your part as is the case with a square turret. And, well, it permits multiple mounting of tools. Here you can see that it's also indexable, so you can turn it around from tool to tool, and, well, you can even take it right off, and you see I have some indexing. Well, I have an indexing pin here that isn't there right now because, well, I didn't want it to fall out, but it will index on those holes, so you can get a reasonable return back to your original position with those indexing holes. So here I have turning facing, slotting or grooving, and a boring bar mounted up in here. So that's just something that I made from a piece of 4140 steel. So just a little home project. I don't have a drawing for it. I sort of made it up as I went along. The next question had to do with this leaf jig, or not leaf jig, but really sandwich jig that we saw in our last video. And the question was, why is the nesting, the location nesting, situated in the top portion? Now you could do it the other way around, but just take a look at this. If I flip it over, as I would do when I'm unloading the tool, the chips aren't present here. Now I open the tool and the chips are going to be here and here. I can clean that easily, unload the part, and when I come to reassemble it, well, I can reassemble it easily because the chips aren't in the threads here. It keeps the threads a lot cleaner, and since I have to turn it over to unload it, well, the chips that may be accumulated in the little spaces that I've left here between the end of the bushings and the surface location, well, that space will empty out when I unload the tool. So it's really a question of chip control here. It could very well be the other way around. I just prefer it this way. So let's get this drill jig out of the way and move on to our next question, or questions, which have to do with the EDM. Now, we had a video where we produced this part. I don't know if you remember, but we produced a hole and a texture here on the EDM. And to do that, well, we used a poco graphite electrode. And it wasn't clear in the video. I really should have made a point of saying it. The dust produced from machining electrodes on conventional machine tools is a very fine and dirty stuff. It is not good for your health. So when you do machine poco graphite to produce electrodes, make sure that you use proper ventilation. My shop has a huge ventilator for its size, and I can really change the air in the shop quickly, which is a good thing. And wear a mask. I mean, it's important when you're machining this stuff. The next question about the EDM had to do about tool wear and dimensions or accuracy of the hole. So let's, to answer those questions, start by measuring the cavity or hole that we produced and our electrode. So if I measure the D hole that I produced, it comes in at 515 thousandths of an inch at the top here, where we started to produce the hole. And if I measure my electrode, where it hasn't come in contact with the part, well, I have 502 thousandths of an inch. Now, that's a difference of 13 thousandths of an inch, or if you prefer, 6.5 thou per side of the electrode. And that's not surprising, that's a big difference. But remember, we were doing this with a roughing cut, so there is going to be a large difference between the electrode and the part. Had I been doing or producing a finishing cut, well, I could have got that distance way down. I mean, close to 1/1000th of an inch. So it really depends how hard or fast you're cutting, the difference between the two. It is important to mention, though, that it is very constant. If I cut several holes with the same power of discharge that I was using, well, I'd always get that same 6.5 thousandths gap. Now, where could that change? If I were cutting a different type of material. Now, most steels will have about the same distance or gap, but if I were cutting, let's say, a bronze or a brass or a copper, well, that gap or the difference between the electrode and the part would be a lot greater, because that material has a much lower fusion point. Now, if I measure this D-shaped hole from one end to the other, well, I notice that I have a 6/1000th of an inch difference between the starting end or side and the end side. And why is that? Well, it's not a gradual taper. The hole is generally parallel, and just at the very end, it sort of rounds out in the last quarter. And why is that? Well, because our electrode cuts mostly on its end, but also slightly on its side. And as that side starts to wear, well, it rounds off the end of the electrode slightly. And that's what gives me the difference in diameter. Now, that is not much of a problem, and generally we would rough and then finish. But what could I have done here to get that hole almost perfectly parallel? Well, it would have been, and you may have noticed that this electrode is way longer than it needs to be. I cut here, and I stopped the cut when the electrode just came out the bottom side, just barely. But I could have continued on quite a bit, permitting a new surface of the side of the electrode, one that hasn't been slightly worn down, to penetrate the full depth of the part, and that would have ensured a much more parallel hole. That, however, doesn't take care of what we call as skip arcing, And skip arcing is when the particles being extracted from the hole create a jump point for the spark and permits the spark to go a little further than it should. It's just when the dielectric fluid gets saturated with particles, it becomes a little more conductive. So what can we do there? Well, the answer to that is fairly simple. If you're doing die work, generally speaking, you would want to pre-drill the holes that you're going to cut with your electrode or finish with your electrode. It saves an incredible amount of time. So you would pre-drill and then heat treat your part and then go over to the EDM and finish the complex shape that you require. And that means that generally you'll have a hole that's already in the part. Now, in my demonstration, I used 2 flushing jets to clear particles out of the way. But we would have had something a lot more efficient if we used the suction jet. Now, you can see on this picture that we have 2 flushing jets and a third one that I didn't use. Well, it is a suction tube that I could position underneath the part where the pre-existing hole is, and I would suck liquid through the part, around the electrode and down under and out the bottom. What would that do? Well, that would mean that I would have fresh filtered liquid coming in from the top and exiting the bottom. Now my cut is going on the tip of the electrode, and that would mean that I would never have particles coming up between the electrode and the hole that I already produced, and really limit that skip arcing. So that would be one solution that we didn't see. Use suction instead of flow to clear out those particles. Another question had to do with surface finish. Now, we have to remember that there's really 2 sides to surface finish. There is surface texture and there is surface finish. Now, the texture is a description and the finish is a dimension in micro-inches. So if we talk about what kind of surface texture we get with EDM, well, that texture is a class P, as in letter P. So class P for pitted non-directional. So that is not a polished finish, it is a matte finish. Now you can get a very fine finish, but it's still and always going to be a matte finish, class P. Now the surface finish you are going to get is about a 63 micro-inch, which is a good finish if you were turning or milling and that kind of operation. So it's at least equivalent to what you can get with traditional machine tools, chip producing. If you're cutting very rough, and that's what we were doing, well, the finish that we got, and here's a picture, is about 125 micro-inches finish. And if you're very attentive and use a finishing electrode and really have a lot of time to waste because it's going to take forever to cut, well, you could get yourself down to about a 32 micro-inch finish, and that would be about equivalent to a reasonably good everyday finish that you would get on a surface grinder. Some people ask questions about roughing and finishing electrodes. And it may be a little counterintuitive because when we rough cut things on the mill, we tend to go for large and strong and rigid tooling. But in the EDM world, a roughing electrode, well, is going to be smaller. And the logic is that when you're roughing, you're cutting with a very intense spark. And, well, that gap is going to be much longer. The spark is going to be longer. And that means that the gap around the part is going to be much larger. Now, if you don't want to oversize your hole, you just want to rough it out for a future finishing pass, well, you would better cut it with a smaller electrode so that the electrode's diameter plus the gap that it's going to create, well, still is less than the finished diameter of the hole. And then your finishing electrode will have a much smaller gap, so it will be a lot larger, or larger I should say, than the roughing electrode. The last question that I want to talk about is, does electrical discharge machining affect the heat treatment of the part? It would seem to be logic to say yes, but it doesn't. Now, electrical discharge machining produces sparks that are intensely hot, but they are also incredibly small. So even though they melt a very small surface, that portion, once removed, cools down very quickly and its adjacent surface. And really, there is no difference possible. So we get very intense heat that's very localized and never comes back to the same spot twice because those sparks are going around all over the part. That means a big surface and very small sparks, no problem. So quick answer is no. EDM, electrical discharge machining, does not affect the surface hardness of the part you're machining. Now, there is one last thing that I'd like to mention, and that is that this is all I'm going to be doing on EDM. But if you want to have a lot more information, I would strongly recommend that you go take a look at a company called Reliable EDM. They're based, I believe, in Texas. They're very easy to find on the internet. They have many excellent videos that explain and describe different types of EDM work. And that includes wire EDM, something that I just can't do because I don't have access to that type of machinery. So remember, that's Reliable EDM, and you can find them easily. So until we meet again in our part 2 of our jigs and fixtures video, that's the next one I want to produce, we'll have fun. Be safe. Wear a mask when you're working with dusty and dangerous materials. And as always, happy machining.